Professor, hello everyone. Welcome back to another DDLC seminar. Professor, it is an honor today to have Professor Gioele Zardini. Professor Gioele Zardini is the Raj and Nancy Allen Assistant Professor at MIT. He is a principal investigator in the Laboratory for Information and Decision Systems, the Department of Civil and Environmental Engineering, and an affiliate faculty with the Institute for Data Systems and Society. Professor Gioele Zardini received his PhD in 2024 from ETH Zurich and holds both a BS and an MS in Mechanical Engineering and Robotics Systems and Control from ETH Zurich. Before joining MIT as a faculty, he was a postdoc at Stanford and held various visiting positions at Autonomy Singapore, then Active, now Motional, Stanford and MIT. Driven by societal challenges, the goal of his research is to develop efficient computational tools and algorithmic approaches to formulate and solve complex interconnected system design and autonomous decision-making problems. His interests include the co-design of complex systems, all the way from future mobility systems to autonomous systems, compositionality in engineering, planning and control, and game theory. He is the creator of Autonomy talks, as well as a lead organizer for the seminal workshops Compositional Robotics, Mathematics and Tools, and Co-Design and Coordination of Future Mobility Systems at IEEE ICRA and ITSC, respectively. He is the recipient of the ETH Medal for his doctoral thesis, the 2025 DARPA Young Faculty Award, a paper award at the 4th Applied Category Theory Conference, the Best Paper Award at the 24th IEEE International Conference on Intelligent Transportation Systems, DOE, MIT, and Amazon Awards. Professor Gioele Zardini, welcome.
Thanks a lot, Panos, for the fantastic introduction. It's long. Every time you read it, I feel I should give you a shorter thing because I'm making your life harder. But this is great. So first of all, thanks both Andreas, but also Panos, Nishant, and Shanting for organizing this seminar series. I actually watched a lot of the talks. It's great to have this platform so that you can learn more about what colleagues are doing. I think you guys are moderating the questions, so feel free to interrupt me at any point if you have questions. You don't need to wait until the end. And yeah, I'll take it away. So my talk today is on this vision I'm working on with my lab here at MIT on compositional design of society critical systems. We'll try to dissect every word of this title. I know it's a kind of an exotic one. And applications today will be mainly in autonomy and future mobility, but hopefully we with some of the people in the audience, we find new applications in domains I am not familiar with. So first of all, most important thing is the work I'm presenting is not only from me, but it's from a group of amazing students coming from different backgrounds. We have people from classic, control theory, dynamical systems, but also operations research, computer science, some in applied mathematics. And I cannot find a picture where we have not just had some meal or are about to get some meal. So this is really something we do well. We treat ourselves well. And I thought of bringing a general slide of what my lab does. We work on a bunch of applications ranging from intermodal mobility systems. When I say intermodal, I mean having various modes that interact together. You can think of autonomous flying vehicles, autonomous vehicles, but also public transit. We do a lot of automated warehouses, multi-agent autonomy. Recently, some work in automotive when we design racing cars, soft robotics, and maritime shipping. And now the first reaction when you look at this kind of weird mix of applications is to say, well, what is that is common in all of these applications, right? Why are these people working on those? The common thing is that all of these, the success of each one of these applications requires coordinating decisions at various levels. I brought this slide to show you kind of what are the many levels. For all of these examples, you can design the single agents themselves, be it an autonomous vehicle, a robot in a warehouse, or actually an autonomous crane in a port. Then you also have to design things at the fleet level, fleet composition choices, layout choices, how you design the network on which you operate, coordination algorithms, you are maybe coordinating 10,000 robots together, and finally also operational choices. So you have to make a lot of decisions that are interconnected. And the societal impact of the technology depends on the joint design of all of these components, not only one in silo. And in this context, if I take autonomy for driving as an example, there's going to be people telling you all things from both sides of the spectrum. There's going to be people telling you, yeah, this technology will solve all the issues. First and last mile mobility will improve. The mobility will be more affordable and sustainable. On the other hand, there are the pessimistic people that will tell you that congestion will rise, energy consumption will rise, and there is also evidence for some of these statements. I don't want to hold parts for any one of these two sides. What I want to develop is a toolbox where while we slowly understand single components, we can put these components together and design interconnected systems. And I want this framework to be both practical, so we can do something with this, but also formal. I want to be able to really create a new language to formalize these problems. And this is really the timeline for the talk. I will be a bit more precise about the problems that actually we want to solve. And now we then show you a framework we are developing to actually solve these new optimization problems. And since we are opening a lot of questions, I will dedicate a big part of the talk also to talk about the outlook and the ongoing future research, because there are many problems we need to solve, and I don't have enough people in my team. We need more people to work on these issues. So as I said, you can find all the papers in this website you see here, and feel free to stop me at any point with questions. Now, to really get started, I want to start with the idea of co-design. What is that I mean when I talk about automated co-design? Automated co-design for me is a very broad perspective. You start thinking about minimizing some resource usage as an engineer. So this could be the energy consumption of your process. This could be the funding you have to invest to make the technology happen. But it could also be the error with respect to a trajectory you have to follow if you are designing a robot. Right? This is some resource you're trying to minimize. And this is subject to the so-called functionality constraints. You want to serve a certain transportation demand. You want to follow a certain trajectory. You have a swarm of drones that want to cover a certain area or find a certain person that's lost in a forest with a certain probability of success. Those are the so-called functionalities. Now, I want to take the task of the designer and have a language in which I can specify this task, specify knowledge from multiple domains, and specify the design options, the actual things I'm deciding between. And I want to automate the task of the designer. So I want some magic to tell me, hey, those are the optimal designs, and this is what you should do for this specific problem. So let's be a bit more concrete. For the case of autonomous vehicles, you want to design the task. You want to specify the task. It could be a distribution of scenarios you have to take into account, also with the probability they will occur. You want to specify robot autonomy and physics principles. You want to specify components and algorithms. Those are the actual things you're designing. Think about sensors, the perception algorithms, the control algorithms. And now what you want to find are the optimal solutions. And those could be in terms of the performance and the investment you have to put in the technology, for instance, or the energy and the errors. Now, if you are interested in mobility, as I know many people are in your lab, you might think about mobility design, right? And here the task is to serve a certain demand. The principles are from networks, operations, and infrastructure. And now the services and policies are the actual things you're designing. And now, again, the trade-off could be in terms of the performance and investment. And you want to look at these multiple possible solutions. Now, why is it hard to come up with the magic inside this box? Essentially, why is it hard to, first of all, find this language, and second, solve these problems efficiently? I'll give you at least 3 reasons. The first reason is that making decisions for these systems requires interconnecting various components at in various different domains, right? If I think about the very specific task of designing a fleet of autonomous vehicles, I have to already decide things at the actuation, computation, perception, control level. Some things are software, I have to develop the right algorithms. Some things are hardware, which sensors, where do I put the sensors, which computing, and some things are kind of in between, like liability and regulations. And the first reaction is to imagine, I have here a bunch of languages. In the US, you would say, oh my God. And some Chinese colleagues would say, walao. It depends, right? Some people might think about different words, but the first reaction is to be totally shocked about the complexity of the system and to say, okay, there are too many components, too many objectives. I don't even know how to understand the whole system. And more importantly, I'm afraid to make new choices because I don't know what the effect of these choices will be on the entire system design. And so the diagnosis for this sickness is that you lack a toolbox for co-design that is formal, quantitative, but also intellectually tractable. And I will talk about intellectual tractability later a bit. Good. So this is one complexity. You have many components and they are interconnected horizontally. Now, not only they are interconnected horizontally, but actually these components also play on a vertical layer, right? So your system is just a component in somebody else's system. That's the slogan. So you can be focusing on designing sensors for autonomy, but at the end of the day, your sensors will be part of an autonomous vehicle where you have to orchestrate various components. And you might focus on a single vehicle, but at the end of the day, your vehicle will be placed in a fleet made of many such vehicles, and you will have to control that fleet. And even if you care about autonomous vehicles only, at the end of the day, your fleet will be integrated in the mobility system, and this mobility system will have to perform. And the interactions between modes will have to be smooth. And now you can even zoom up and down again. You can zoom out and think of interactions of mobility and energy, or zoom down and think about sensors and chips, the design of chips for particular algorithms, and so on and so forth. So the bottom line is you have horizontal and vertical interactions. And finally, you also have interactions in the context of having multiple stakeholders. So imagine you want to design a mobility system in Boston. It's not only about academia and tech developers, which is represented here by my president, Sally, but it's also about all the other stakeholders, policymakers, industry, liability, mobility providers. And these people speak different languages, first of all. So you have to find a language that puts all of these people at the same table, but also they care about different objectives. And these different objectives really require new techniques to actually to find agreement, right? So this is the third complexity. So to summarize, you have large systems, many components, many scales, different natures. So you have to put together different disciplines and multiple objectives. On the other end, you have potentially many agents, heterogeneous interactions, and conflicts and collaborations. Now, if you design a toolbox that deals with this, my 6 golden rules are the following. Everyone that works on co-design in my lab has to remember these rules every morning, and every evening they have to repeat the rules. It's, the toolbox has to be formal and domain independent. You need to make sure that whatever you design accommodates components from different domains. You don't want to over-specify for a specific domain. Second, it has to lead to something computationally tractable. I'll tell you more about it later, but we need to be able to solve problems in reality, in practice. And we need to be able to talk about these composition and hierarchies, right? So compositionality and hierarchical, meaning horizontal and vertical composition, are things that we want to be able to model naturally. It needs to be able to allow collaboration. So you need to be able to pool knowledge from different experts, for instance, in this audience, and put it in the same framework. But also it has to be intellectually tractable, right? Sometimes to have something that's collaborative, you have a system architect that goes around and knows everything about every subsystem. You don't want that. You want something that's kind of distributed where people can actually contribute to the entire design. And finally, it has to be continuous and adaptive. So it has to be something that you can change over time. Good, so this is the premise. And now I want to show you exactly how you can deal with these problems and how you can aim to solve some of these problems. And I will also try to show you what the challenges are in this effort. So the toolbox I'm going to present, it's a toolbox for co-design, where co is a branding for collaborative, computational, compositional, and continuous, so a lot of co's. And this is a framework that essentially leverages domain theory, applied category theory, and optimization, and will allow you to, first of all, formulate these problems and then solve them. So within the next few slides, I will be very precise and telling you what the design problems are, what the constraints are in these kind of problems, and also finally how to actually solve these problems efficiently. So by the end of this first part of the talk, you will understand how to go from this diagram on the left, which represents here a design diagram for an autonomous drone, to the Pareto front on the right, where you actually look at uncomparable optimal designs when you try to minimize the tracking error and the power consumption of this drone. Now, you might wonder why you've joined such a talk when somebody's talking about domain theory and applied category theory, very exotic and random topics. I have two good news for you. The first good news is, well, you don't need to know anything about this topic to understand the talk. So the talk is user-friendly. However, if you know something about these things, I will hide some Easter eggs in a so-called pro box. The second good news is if at the end of this talk, I convinced you that this is stuff you would like to learn, on my lab's website, we have my class material available in form of slide. And we also have a book that we are going to publish with Cambridge University Press, and we have the draft online that you can access, and you can start learning about these topics from scratch, assuming zero background knowledge. So, and if by the end of this talk, you realize you don't like this stuff, you're free to not look at this anymore going forward. Good. So to really get into the topic, to think about design, you think about three spaces. Every time you are designing something, there is the so-called implementation space. Those are the options you can choose from. Those are the things you can design, right? It could be a sensor, it could be a parameter in an algorithm, it could be the algorithm itself. Now, they exist because they provide some functionality, right? They provide some desired behavior. And providing some desired behavior requires some cost or requirements, right? As I told you before, providing satisfaction of travel demand requires investment cost, requires emissions, requires time, these kind of things. And now, depending on the domain you are from, you may already know these terms with other names, right? You might have functionalities, which are desired behaviors, specifications, objectives, guarantees, and you might have costs instead that are budgets, requirements, dependencies, or assumptions. Now, the key thing is I want to be able to model trade-offs. And I think in our discipline, we're not used anymore to thinking about multiple objectives, right? We are bombarded with new computing tools that work very well with single objective problems. And we kind of forgetting that engineering is full of trade-offs and it's full of Pareto fronts. So in this talk, I will talk about requirements as something that is first of all, is represented in red. And you can think of it as something between it's free and it costs a lot. And technically, you want to minimize the requirements. Functionalities are something you want to maximize. And you can think of this as between does nothing and does it very well. You prefer this to be very high. And a nice challenge for anybody in the audience is to open any engineering book and find trade-offs. You could have many forms of trade-offs. You could have two costs, and everything above this so-called Pareto front is feasible, but you don't like it. Anything below, it's a dream, but it's not achievable. And what's on the curve is actually the best achievable trade-off. You could have the same thing with two functionalities, and just the situation is reversed. Or you could have this interaction between costs and functionalities where you have a monotonic curve. Now, another way you might know already trade-offs is as a student, as a PhD student, you have to choose two among three things: social life, quality of your research, and sleep. I think those are the three. So you have to choose two, right? You always have to find trade-offs in your life. Good. So I'll come back to this later, but I want to give you some intuitions about these trade-offs and the implementations. So a nice example, since we are in the sports season, although this is not really the winter one, you could think of a trade-off between speed and strength for the human body. Usain Bolt is very fast, not so strong. Oleksiy Novikov is super strong, not so fast. Both are faster and stronger than me, and I sit here in the bottom, clearly dominated by the two. But there might be somebody that is not as fast as Usain Bolt, not as strong as Oleksiy Novikov, who still sits on this theoretical Pareto front of what you could achieve physically, right? And now I want to bring an example to actually clarify these implementations, resources, and functionalities, because I think this is, although intuitive, this might be a bit strange if it's the first time you look at it. And since I'm Swiss, I can either bring an example about watches or chocolate. So I chose watches for this specific one. You have two implementations. Those are two products you are designing, a Casio F91W and a Patek Philippe. Now, what could be, usually I do this in an interactive way. I know here I can only be interacting with the three of you, not the whole YouTube audience, but let's make this interactive. What could be some resources for these two products? What do you think could be something you might care about when comparing these two products? Shanting, I see you want to say something.
Yeah, I would say the second now, like if it align with outfit.
Outfit, okay. Okay, I cannot modify the slides on real time. So outfit is not something I thought about. But let's be very practical. If I tell you, hey, you have to buy one of the two, what's the first thing that you notice if you think about the resources or requirements?
Maybe budget.
It's where I'm from, we do this sign, right? We spend, it's about the money, right? So one is price, one is cost a lot, and one costs much less, right? We don't want to put numbers, but that's kind of a relation between the two. Good. Now, what is a functionality? Shanting, you hinted at a functionality. It's if it matches your outfit. That could be something that this product provides to you. I don't have that, but you could do that. Another functionality is these are watches, right? So what does a watch do? It tells you the time, or it allows you to set multiple alarms, for instance. Now here we have an interesting one, which is the Casio allows you to tells you the time, but also tells you multiple alarms. Whereas the Patek Philippe only tells you the time, right? So I told you before, we look into minimality when we are trying to design, we look into the trade-off. So initially, when I look at this example so far, it might seem that there is no absolute point of buying a Patek Philippe, right? Because it costs a lot and it only tells you the time. Whereas you could get something that costs much less and tells you the time plus multiple alarms. Clearly, since the two products exist in the world, there is this law of successful products that tells you that there must be something else people care about that actually allow you to disambiguate between these two products. And Shanting mentioned one that is interesting, could be whether it fits with your outfit or not. Another one could be signaling, right? For instance, I could say I am somebody who can afford a Patek Philippe, and I chose to buy one. If I'm an engineer, as many of us probably in the audience, we like Casio F91W because it's nerdy, right? It's cool. So maybe we want to signal that we care about these things. But maybe the quick take-home message here is, even if the example is super simple and we have only two products and a bunch of, and only few resources functionalities, you see that already comparing things becomes quite hard, right? So imagine when doing this for an interconnected system with many components, with many different trade-offs. And by the way, I'm not the first one to talk about these things. I like to bring this picture recently in my talks, and especially when John is in the audience. There's people talking about trade-offs for many years. In this particular talk, John was talking about trade-offs between fast and slow planning and all the other actual properties, like being accurate, flexible, centralized, conscious, and so on. And it's I'm very happy to see that these things are slowly coming back to being interesting, but looking at these trade-offs is very important. Now, how do we model trade-offs in practice? We model them through the so-called partially ordered sets. Partially ordered sets allow you to model standard costs in engineering, which are so-called total orders, where you can always say that you prefer something over something else. For instance, real numbers. If I'm talking about energy, I can always say that 10 is more than 9, that's more than 8, and so on. There's always a relation between these numbers. Natural numbers is the same. But sometimes you might have things that are uncomparable, right? For instance, you guys, some of you are in Ithaca, you might have a partial order of the gorges, which is one of the highlights of the region. And you might say you prefer Cascadilla over Taganrog Falls and Buttermilk Falls, but you don't prefer one over the other, right? You actually leave the degree of freedom. If you are into motion planning, you might have a priority over some metrics through which you evaluate trajectories. For instance, think about collision energy, the area violation and clearance, and now think about a bunch of trajectories that you want to rank. Now, this priority that you have over certain metrics allows you to rank these trajectories in different ways, right? So the motion planner can use these priorities to then make a selection. In this case, you have an obstacle, a clear Swiss obstacle. You have two trajectories, B and C. Those two trajectories are kind of symmetric around the obstacle, so they don't have collision energy, they don't have area violation, so they don't go in the other lane, and they have some clearance. Trajectory A has a lot of collision energy. In fact, you are colliding into the obstacle. And trajectory D instead does some area violation to keep along a higher distance from the obstacle. So in terms of this partial order, clearly trajectory A is the worst in this case. But then you have area violation and clearance that are uncomparable. And that's why you have one option is to take either trajectory B or C that stay very close to the obstacle but do not violate the area of the other lane, or you choose to violate the area on the other lane and you keep a larger distance to the obstacle. In this case, they are not really comparable, and so you have this degree of freedom. If you are from controls or information theory, you can think about matrices, positive definite matrices, as ellipsoids. You can represent these ellipsoids based on the eigenvalue or eigenvector decomposition. And now you can order these ellipsoids by inclusion, right? If one is contained into another one. And for instance, this could be a nice metric when you want to compare uncertainty. If you interpret these as covariance matrices, this is a way to think about uncertainty. Another example of things you could do with partial orders is, say you want to create a partial order of pairs of sensors and algorithms for the task of detecting a passenger in front of your car. Now, clearly, every pair of sensor and algorithm has different performance metrics. Those could be measured as false positive, false negative, and accuracy rates. And those are curves that depend on the distance to the obstacle. And now you can order these curves based on dominance. And now this becomes a certain partial order of these curves. And then you can even bring these partial orders and bring them all together into a combined partial order. Now, I don't want to go into the details of any of these examples, but the idea is you can be very quantitative comparing things and quantities of interest with partial orders. And from now on, I will think about functionalities and resources as partial orders, where in the case of resources, you want to minimize them. In the case of functionalities, you want to maximize them. Now, the second key concept to understand design is that there are implementations, functionalities, resources. And the key question you want to answer is whether, given a certain functionality or a certain desired behavior and a certain resource or a certain budget you have available, there exists an implementation you can design that gives you at least the functionalities you want by requiring at most the resources you have available, right? So this is what I call a design problem or a feasibility relation, right? This is how I specify the design problem of a certain component. You are given a certain functionality. Could be, I want to cover a big warehouse area and find a gas leakage. And I have available, $1 million. Is it possible to build a system that does this? Yes or no? And that's the answer, the Boolean answer. This is what's called a design problem, and it's in technical terms a Boolean profactor. And it is a monotone map. Why? Because if I lower the functionality, it should not require more resources. If I have a solution to cover a warehouse and I suddenly say the warehouse should be smaller, it should still be possible to cover it with the same budget. On the other end, if I suddenly have more resources available, so if I increase the budget in this case, it should be possible to provide, it should not be possible to provide less functionalities. Now, here I made an example with one functionality, one resource, but remember these spaces can be anything as long as it's ordered, right? It could be the combination of very complicated spaces. So the first reaction is to say, okay, good. You tell me that now I can model these design problems for the components as these feasibility relations. And by the way, another thing you can do is design a box like this one with green wires on the left for functionalities and red wires on the right for resources. And now the question is, what do I do with it? It feels kind of very abstract and exotic, right? What you do with it is you populate these relations, right? In practice, you might have some existing designs. For instance, you have a suite of drones and you have different properties of these drones. For instance, the flight time, the range, the camera, the size, and so on. In some cases, you don't have the actual components themselves, but you have some first principles or some laws that your system has to obey, some physical laws. For instance, the mission energy is for when you design a drone, it's always greater or equal than the duration of the mission times the power consumption. And that's always true, no matter which drone you look at. Or in almost every example I will show you today, you actually have this data-driven or on-demand modality where you just have a sequence of data points. It could be that you have these feasibility points that are given by an experiment, a simulation, an optimization problem. It doesn't matter, but these points actually form a feasibility relation. So again, to take a step back, you have implementations, functionalities, and resources. You look at every component and you think about the feasibility. When you have the degree of freedom is the design you are trying to produce. And the question is, can I achieve the functionality I want by paying at maximum the resources I have available? And the way you populate these possible designs is with these three modalities. So this is where we are so far. And my punchline, I think, is that you can use this to model almost anything you like in the application you care about. So I hope that after this talk, you're able to draw a box with something you like. And here I brought just a selection of some of the things you could do. This is a trivial example of a Swiss researcher. If you give it chocolate, it will produce papers. Here I'm talking about quantity of papers, not necessarily quality of papers. But you name it, right? You might be from controls. You can think about linear quadratic Gaussian control as designing something that is robust to some noise and minimizing some error and effort. If you are into assume guarantee contracts, this is Alberto Vincentelli from Berkeley, a friend who, you can model these assumptions and guarantees as sets, and the order is inclusion of sets. And now guarantees are something you provide and assumptions are something you require. If you are in operations research, there is this famous problem called the bin packing problem, where you're given a container shape, you're given some content shapes, and you have to fit the content shapes into the container shape. Now, if I make the container shape larger, it means I increase the budget, the problem becomes easier, right? In a sense, I'm relaxing some constraints. If I make the content shapes larger, I'm asking for more. I'm making the problem harder, right? So I'm adding more constraints. If you are into multi-agent systems, you could think about a general performance metrics such as the area you want to cover. And now you pay by paying the speed at which each agent has to drive, the number of agents, the time needed to cover the area, or the total cost. Now, there are many examples, and we can argue about how you put the wires. There's a lot of freedom there. But I think one thing we can argue about is you will be able to design a box like this one for something you care about. And the reason why I'm very excited about this framework is that not only you can design boxes, but you can interconnect them in many ways. You can put two boxes in series, you can put them in parallel, you can have a feedback operator between them, you can choose between two options, or you can try to convince two experts. And no matter what you do, you end up with something that has the same properties of a box. So the property of being a box, so the property of being a feasibility relation, as I presented before, is preserved, right? And this becomes a very important tool. This is essentially gives you a closure, an algebra of interconnections with closure. And this is very cool because it allows you to decompose large problems into subproblems. And you can do all of these at the graphical level, without worrying about writing down the formulas for each of the blocks, because there is a calculus of diagrams, so-called calculus of wiring diagrams, that works if you have in the background something that's called a category, which has some properties. That is trace monoidal and local positile. So if you're interested in this, you will learn about this in the book. Good. So to take a step back, we have something that is formal and compositional and hierarchical by nature. I can model components and I can model networks of components. Now, since I know there's a lot of control theorists in the audience, I want to clarify what I mean when I say that you can have feedback operators. This is not necessarily the same feedback you're used to when looking at a classic signal flow diagram. When I think about feedback, what I think about is you have a drone. The drone requires actuators to move. The actuators must be powered by a motor, by a battery, and the battery must be carried by the drone. Now, if I need more actuation, I will need more power. But more power means a heavier battery, and the heavier battery will require more actuation. So you have this kind of self-reinforcing loop in the design. And the same goes for computation, mass of your system, the power consumption, or the uncertainty that adds to itself, right? If you actually don't want to even look at the physical interpretation, you can even think about engineering versus business case, right? Think about you're designing a new mobility system, you are investing some money, and you want to make sure that you get back through selling your service at least a percentage of whatever the investment was. That's kind of a feedback loop of your design. Good. So now I want to make the case for applied category theory. If you have followed what I do, or you start following what I do, I talk a lot about applied category theory. We organize a lot of workshops, as Panos mentioned in the introduction. And I want to kind of give you my 2 cents of why this is important. Then again, you're free to disregard, but I think it's very important. It's a very important discipline to look at. So my case is the following. Right now, you have developed very good mental models for systems and components in your domain, right? Some models are very formal. Some are kind of informal. Some models are used for you to actually compute things. Some actually are not used to compute things, are just an abstraction that you use to think about your systems. Typically use the formal models to design, simulate, and analyze your system. Think about partial differential equations as an example. And also the formal models help you communicate and share your ideas. When you write a CDC paper, deadline is in 1 month, so you probably are doing this, or ICRA, right? Those are conferences where you actually write your paper and present your ideas. Think of all of these mathematics as a set of patterns you are using to describe the world. So you have all these grammars and you use it to describe your world. Now, there is an unfortunate fact that we are engineers in the 21st century. The engineers before us have solved a lot of problems, and the new problems we have to deal with have by nature to deal with complex systems, architectures, interactions, interconnections. Sometimes some things are designed by someone else and you have to deal with them as a black box. Sometimes you have some uncertainty quantification. So this is essentially the systems we have to deal with. And you can think of applied category theory as a set of mathematical patterns that is designed specifically to describe large systems with complex interactions. This is a field of mathematics that is designed to interconnect knowledge. So I want to tell you what is that it can do for you and what is that it cannot do for you. What is that it can do for you is the following. So it's a mathematical theory, meaning you create libraries of theorems and methods that you can reuse. And the very nice thing is that it's not only formal, but also you have a visual language to think and reason about your systems. So for instance, in this diagram here, you could represent a network of dynamical systems interacting with each other, but the very same diagram could be representing a co-design problem where you're trying to solve 5 different optimization problems that influence each other. Or it could be some verification scheme when you have 5 components that have to behave in a certain way. It might be that the application is changing, but the underlying math is the same, and you can reuse concepts you have learned. So this is very powerful. What is that it cannot do for you is it cannot, and I will add that yet because we are working on it, but it cannot yet solve problems for you, right? It will help you formulate a problem well, but it doesn't necessarily solve the problem itself. So it's not something you can add to your Python script as a one-liner that will help you solve a problem. It's rather something where you have to invest more time at the beginning. You learn a lot about the framework, you learn about the math, exactly as you did maybe for control theory. And then the payoffs comes later. Actually, I wish I learned about this much earlier in my career. And today I will try to show you some points, cases in point. First of all, the modeling toolbox actually builds on this category theoretic knowledge. The solution of these problems, which is my next topic, actually exploits these compositional structures. And actually, we have some work we are working on right now that shows you how it's easy to actually extend the structure once you have these formulas. So the other drawback is that this math is kind of unfamiliar to some engineers. And the typical books you find out are for mathematicians, computer scientists, or software engineers. In fact, there is a joke in the field that says, with which book did you learn category theory? And people say, oh, the 7th or the 8th, because you never learn it on a single book. You have to read many books. So that's why we started creating a class and a book to actually fix this situation together with colleagues at ETH. Good. So this is my 2 cents on why category theory is cool, but now I'll actually show it to you. I built the climax on, hey, we can build these problems, we can model them, we can have a network of problems. Now I want to show you how to solve them, actually how to get to solutions. And here the notion of solution is maybe slightly different from what you have heard before. And here we have essentially 2 queries. The first one is you are given some functionality at the system level, and you want to find all the solutions that help you minimize the resources. So if we go back to the example of the warehouse, you want to cover a certain area in a warehouse, you want to minimize cost, energy consumption, find me all the components of my system. It could be instructions for humans. It could be fleet design for a robot. It could be control algorithms for the fleet, such that I minimize these resources. On the other hand, you could be given the resources that are available to you, and you try to maximize the functionality you can get out of those resources. Those are the two queries. They are dual in the optimization sense. And in practice, what you want to find, if you go with the first one, is a map from the space of functionalities to anti-chains of resources, or to uncomparable minimal solutions in the space of resources. Okay, so the first thing to do here, since the setting is a bit weird, is to formulate this as an optimization problem. This is a class of optimization problems where you essentially fix a multigraph of problems. That's what's given to you, where the nodes of this multigraph are the design problems, or are these optimization problems, and the edges are the dependencies between these problems, these various interconnections I was talking about before. There are variables that are these partial orders for functionalities and resources, and there are two kinds of constraints. First, each node, each design problem, has to have this notion of feasibility I introduced in previous slides. And second, each time you see this constraint, each time you interconnect two systems in series, you're saying that the resources required by a box should not exceed the functionality provided by the second one. Right? If I have an algorithm that requires compute, it can never require more compute than it's given by the chip. Right? This is a limiting constraint that you have when you are designing system. And now the objective at the system level is to minimize R, which is the resulting resources at the whole system level. So this is a very strange formulation, I agree. And on top of that, I have more bad news, which is this is not convex, this is not differentiable, it's not continuous, and actually not even defined on continuous spaces. So if you work on optimization, you just change topic, right? You do something else. But I want to show you that actually there is hope, and you can solve these problems rather efficiently. And the magic behind this is a compositional approach. So in my class, I use a couple of classes to actually teach this very specific concept. Here, of course, I have a handful of minutes, so I want to give you the gist of it. The idea is that starting from the components, where it's easy to find these local H maps from functionalities to anti-chains of resources, you want to find the entire map for the entire system. And one theorem you can prove is that you can solve the composition of problems as the composition of the solution of problems. So this means, although since I'm playing with words, this simply means that for all the composition operations I defined for the problems, I can find the equivalent composition operations for the solutions. I can find it in a constructive way that gives rise to a least fixed point algorithm. A very strange one, but it's a least fixed point algorithm. And I can do that because I have a functor between these two categories. Again, this is the value of having this formalization I presented before. And this algorithm has two cool properties. First, it's complete, meaning you can find the set of all optimal solutions if any solution exists, or a certificate of infeasibility, right? If I say I want to be in the next 10 minutes in Ithaca to have a coffee with you guys, it's infeasible, for now. One day maybe it will be feasible, but now it's impossible. The second important consequence is that the complexity of solving these problems is not combinatorial in the number of options, but it's just linear. So this means that when I want to solve an interconnection of many problems, the complexity only scales linearly with the number of options. And this is huge news for us because we will interconnect very complicated problems. Now, of course, this is not all amazing, right? Because there is a catch. The complexity depends on the interactions between components. And that's something you will never be able to get rid of, these feedback loops. And I will show you that this could be a concern. Good. So this is the punchline, the second punchline. So it's something that is kind of computationally tractable, although I have many things, many tracks in my group where we are working on actually making this computationally tractable. But this is a good result. And the other good news is that you don't necessarily have to learn about category theory or details of co-design to actually use this. So exactly as you maybe now use CVX to solve convex optimization problems without necessarily knowing exactly what the method is that is used in the background to solve your problem once you specify objectives and constraints and so on, you could have a similar approach to co-design. There is a language to specify the components the design problems, and there is a solver. Of course, this is it's not as powerful as industrial solvers, but it's something that we're working on, and it's very, very cool if people want to try and play with it. So now I want to show you, I know I want to be cognizant of time. I want to show you essentially this tool at work on some applications. And to do that, I first have to clear out some things. First, when you look at my co-design diagrams, it is tempting as a control engineer to think about those as signal flow diagrams where you have a flow of information. Sensors produce data for an estimator that produce estimates for a controller that produce a command and so on. Actually, when you look at my diagrams, you have to think about the reverse order. You have a decision maker that requires a state estimate, that requires sensing, algorithms, and computation, that in turn require a sensor, programmers, and a computer, right? So this is a requirement or logical dependency flow. And the other thing you have to really get used to when you use this framework is that there is not a single way to model these problems, right? It really depends on what you care about. If, for instance, if you're modeling an autonomous vehicle design, if you are a mobility planner, you might only care about speed versus costs. If you are an engineer in an autonomous driving company, you might care also about the risk, the distribution of scenarios you will encounter, the complexity of the tasks, and so on. And the idea is to first write these boxes without really thinking about what the actual implementations will be. Try to understand at the core of your problem, what are the most important wires you care about, and only later think about how you're gonna populate the boxes. Once you have these diagrams, you will populate the boxes with these different options, right? And I want to clear out some things. First of all, if you're unsure about a component, it's very easy to embed assumptions. So far you can add best and worst case or anything in between, but now we also have a paper where we show that you can do this with distributions of components where you're really not sure. Another thing is you don't need to use this necessarily for components that already exist. You can use this framework to do what-if scenarios. So how do you do this? Essentially, you substitute a component with a possible future component and ask the question, hey, what if I design a component with these functionalities and these resources? Would it change the state of the art for this big interconnected system? That's a question you might ask. And although we do all of this in my lab, still, you could have decentralized design, right? Different people from different parts of the world, different teams could contribute to different components asynchronously. So it is continuous, collaborative, and intellectually tractable. Now, I want to show you first a toy example and then a bunch of more serious examples. The toy example is the following. Think about urban driving as a task of following a trajectory. It's a simplified one, right? The following at the trajectory is a mix of lateral and longitudinal control. And longitudinal control is a mix of speed tracking and emergency braking. This is a possible way to look at this simplified task. And now you can come up with components for all of these designs. You have to design the controllers, you have to design the algorithms that implement the controllers, you have to design the perception algorithms, the computers, and so on. And now, depending on the discipline, you might use different techniques to populate these boxes, right? You might use, in the case of control, simulation or optimization. In case of computing, it's a catalog of chips. In case of perception, is a catalog of benchmarks. So it really depends on whatever is your domain. But what I want to show you is that once you have populated these options, I can actually fix a particular task. In this context, expressed as a particular maneuver you are performing with a certain speed and a certain curvature. And I can find for that particular maneuver optimal designs in terms of the objectives, for instance, control error and cost, or control error and control effort. The first thing to notice is you have different optimal points. It really depends. And the second thing to notice is that actually for each point you can extract the actual design. So which controller to use, which sensor, which perception pipeline, and so on. And if you want to visualize monotonicity, you can think of the complexity of the task or the functionality as being curvature and speed. And the more I increase the curvature and the speed, the more expensive it becomes to actually operate the vehicle in terms of effort and error, right? Now, of course, this is a toy example, but we are moving towards serious and large-scale applications. This is last year's Transactions on Robotics paper, where we show how to apply the same ideas to designing an autonomous vehicle together with planning and perception. This is work led by Dejan Milojevic. And you have, here similar trade-offs, but now you also are allowed to decide how many sensors to place, where to place them, which orientation. And in the future, we're going to be able also to tell you how to operate the sensors over time. But now, if you came into this talk with the society critical applications in mind, you might be a bit disappointed, because so far I only talked about one single vehicle, and I really didn't touch the entire society scale issues. And I want to show you now that a lot of what we do actually is applied to mobility as well, where now the task is to serve some demand and to minimize some resources. And now the things you are designing are mobility solutions and intermodal networks. So in the very same way, you can model this problem as an interaction of different modes. And now you, as a passenger, you can jump on and off each one of these modes. And the modes we consider for this case study were autonomous vehicles, micromobility solutions, and public transit. You can come up with a similar co-design problem, where now you are designing each mode, but also their interactions. And now the functionality at the system level is the demand distribution, and the resources is the total cost, the externalities you are paying, for instance, CO2 and average travel time. And now when you solve a specific problem, if you instantiate this, for instance, in Washington, DC, with realistic network data and realistic cost and so on, you find trade-offs for that specific scenario. Here, the trade-offs are in terms, for instance, of average travel time on the y-axis and investment. Of course, as you pay more, the travel time goes down, but there might be a point where you don't want to pay that much to have that little of an improvement. And now the cool thing here is that each point now gives you the number of vehicles you should use in your fleet, the speed at which they should drive. But since we are embedding these models in a vertical sense, I can also now give you details about the autonomy stack of these vehicles. So I can design everything from the software of a single vehicle to the policy recommendations for a large system. And while I don't want to make decisions myself because I'm an engineer and not the policymaker, I think that going toward more transparent curves like this one is very helpful when people are thinking about designing these systems. Good. So this is something we have ongoing with SIDARA and the Department of Energy grant, where we are trying to bring this to city scale for various cities in the world, where you also maybe combine different aspects of mobility, energy, water, and so on. And now going back to this slide, we are kind of applying these tools to a bunch of applications in different domains that share a similar layer of complexity. You know, have components, objectives, and so on. And one thing I'm very excited about is this recent center that's launching soon, that I will be leading, on compositional optimization for multi-agent autonomy. So the idea is to really specialize this framework to the case of multi-agent systems, and do this with all the details of those technologies. So you will be given a task, and you want to, at the same time, design the best fleet, the best mix of robots, design the robot themselves, but also understand how to coordinate the robots. And here you need expertise from a bunch of different domains. I think I have a world-class lineup of people in the grant, ranging from Aaron to George, Nick, and Ali, and Alberto, all active in different areas of this compositional viewpoint. But I'm very excited about this because I think multi-agent systems will be a great application of these ideas. And there are a lot of trade-offs, right? A basic trade-off I can give you is how many robots should we have? Should we have many simple robots or few very capable and sophisticated ones? How does the answer change if you have compute limitation, or if you have a lot of uncertainty, or if you have energy limitation, and so on? And, you know, to give you a sense, this is current work we are doing with my PhD students, Meshal and Eugene and Max, who visited my lab from ETH to Zurich. The simple instantiation is what I told you before. You have a map you want to cover, and you want to design the best system that covers this map. When I say the best system, I mean the best single robots, the best fleet, but also the best algorithm that controls the fleet. And you might start with a bunch of state-of-the-art planners, state-of-the-art robots, you know, drones, ground vehicles, fixed sensors, and so on. And you want to come up with the best mix of all of these things. This is a very complicated problem, but it turns out it's a co-design problem where you can, again, think about the composition of the fleet, the planning, the execution of the plan, and evaluation metrics. And you can come up with very similar trade-offs as I was showing before, where now you have a cost you are able to pay and the time you need to cover that area, or the energy you need to cover that area. And you can look at the various differences if I increase the warehouse, or if I change the layout, if I make the layout harder to cover, and so on. So there are a lot of nice trade-offs to study there. And this is by no means limited to this toy application. We have ongoing collaboration with Amazon Robotics, where the idea there is how do I design the entire warehouse together with the coordination strategies for the agents. We're talking about thousands of robots simultaneously coordinated. We have similar ongoing efforts with the Port of Singapore, where we're trying to think about how to redesign the port for autonomous operations to improve a bunch of performance metrics they care about, for instance, throughput and so on. And a kind of exotic application with SD is looking into designing the plantations together with the harvesting technology to make sure you don't waste any resources. And all of this is part of a bigger picture, which is a lot of these systems share these various choices, the design of the agent, design of the fleet composition, design of the layout, coordination algorithms, and operational choices. And people really consider this in silo. So you will rarely find people that try to find the optimal designs at the interaction of these ones. But I feel that we should really, going forward, since these systems become more involved in our lives, I think we should really start looking at these interactions. And now this brings me to almost the end of the talk. I didn't talk about a large chunk of my work, which deals with the case in which you cannot control all of the boxes. In practice, a lot of different stakeholders will have access to different boxes, and they might not have the same objectives, right? So you have a version of this, which is what we call the co-design games version, where instead of looking for optimal designs, you're looking for equilibria, or for situations in which no agent, or Pareto fronts in which no agent has an intention to switch. And there are many complications to get to that framework, because first of all, you need to be able to solve games with this new structure. Those are what we call partial order games, which is an ongoing work. And another interesting aspect is that a lot of these games feature a lot of interactions that are kind of hierarchical in some sense. And so you have to develop new computational tools to deal with these huge hierarchies of interactions. To give you a sneak peek of this line of work, we have a recent work from my student Minja, who works on co-designing transportation networks where you have different partners that are trying to not necessarily collaborate, not necessarily compete, but have a mix of the two. So she designed this game theoretic framework where you can both compete and collaborate at the same time, and you can show that this is better than doing one of the two only. And this is something that ended up on MIT News recently, and it was very, very cool coverage, I think. So to go back to the end of my talk, I want to actually show you what I envision for this. I really envision systems engineering of the future to work kind of like I presented today. So you have a bunch of stakeholders that have objectives and components. You use some modeling framework that allows you to interact and model all of these components interacting together. Some components will have very precise models because they come from researchers or engineers. Some will be more high level, will be like spreadsheets, maybe from some practitioners. It doesn't matter. At the end of the day, you will be able to observe the trade-offs, and you will be able to actually test the things in practice, which is an aspect I'm still working on, and then measure whatever you have tested in practice and go back to the exercise of designing and changing a bit the design exercise. And here is where I see a lot of potential also for automating this with new AI technologies. So this is where I want to go. And to get there, there's a lot of problems to solve. Here I thought of mentioning just maybe a couple of them. One is, how do you deal with uncertainty? And right now we have a framework that essentially extends all of these to the case in which you have distribution of components. We can compose this distribution, And this gives rise to super interesting problems, from stochastic optimization to how you sample these problems online, how you learn the parameters from the experiments, and so on and so forth. So this is a very exciting new era that we are exploring. And in general, my group focuses on the algorithmic foundations. So, trying to make these algorithms more efficient, trying to connect to the existing state of the art, but also trying to also solve these co-design games. And the applications are also an important part that really motivate what we do. And here I showed autonomy and mobility, but really trying to branch out and apply this to various disciplines. And the final layer is user-friendly tools. I would like that my tools are not only in academia, but go out in the world and are used and actually benefit society. But for that to happen, we really need to go out and evangelize on these new techniques. And so if you go on our website, you will find a lot of material, a lot of workshops, a lot of dissemination material. So I really encourage you, if you find anything, if you find that we could do better on some aspect, please give us feedback, because I really want to improve on this side. Good. So if you go on with any take-home message, the systems of the future really require a new toolbox for systems engineering that is intellectually tractable first and foremost, but also computationally tractable and compositional by nature. I think we have an edge there. We are close to getting something that is competitive, but we need more people and we need more community around these topics. So I'm very happy to take any questions, and I'm sorry if I went a bit over time. I hope that's fine for the audience.
Thank you very much, Professor. That was truly interesting. We have some questions on the chat. First, from Professor Andreas. In many problems, we distinguish between static design parameters, for example, network structure, sensor placement, actuation layout, and dynamic control policies. Can categorical formulations naturally encode this separation between design and control strategy and still allow joint optimization? Or does compositionality implicitly assume a fixed control strategy?
That's a very good question. Thanks, Andreas. We'll discuss in a couple of weeks when we are here together in Boston. But I think the question is great, and the answer is the first one. So you can model these things. You can model and solve these things simultaneously. You can also model different time scales in the same scale, right? In the same framework. So for instance, you could start asking questions for, what's the best design if I were to look at the next week? What is the best design if I have to use it for a year? What is the best design if I have to use it for a month? And different control strategies might be the best ones, depending on, maintenance needs of your infrastructure and so on. But really the powerful aspect here is that we don't discriminate between these time scales. You can have both things. Now, of course, what Andreas brings to the table is an interesting problem, because in practice, some of the decisions are harder to reverse than others, right? If I design the new port of Singapore and I build it, I cannot unbuild it if the demand changes, right? So I have to allow some degree of modularity when I build it to account for whatever it's coming in the future. A good example is Amazon, that when you have these shelves, you can essentially remodel the shape of the warehouse and the corridors based on whatever the needs are at the moment. But I think there are a lot of open problems there on planning and operations co-design, because the two are typically treated in silos.
Thank you very much. Can I ask a quick question?
Sure.
It seems to me that your approach of optimizing in a much bigger scale, do you see this joint optimization of a lot of stuff will lead to new solutions that we have not expected, or even counterintuitive optimal solutions to some problems?
Yes, that's definitely a good question. Yes, it's hard now to tell you some examples without going in the details, but you definitely see those because by nature when you fix everything but a particular component, you are kind of in the optimization of local minima for the entire system, right? And this is a bit of an issue when you're trying to look at large systems. For instance, I'll give you the example of Amazon. If I have a fixed warehouse and I only care about throughput, I'm going to design a controller that allows me to maximize my throughput, right? But now if I suddenly change the corridors, of course, that maximum achievable throughput will change, right? So the solutions I might find with a fixed network configuration could be totally different than the ones where I actually allow that as a variable, right? So definitely you will find a lot of counterintuitive solutions. One thing we're working on is creating some benchmarks where people can contribute to some components and now see how their particular algorithm or their particular component changes the state of the art, and see if whatever they are doing has an impact on the system level result. But it's not easy, right? Because you have to find an application and an interface where everybody can really pitch in. So, but I'm happy to discuss offline if you have any ideas.
We have another question from Something. Something, would it suit you to read it, or you would like to open the chat, to open the mic?
Okay, I can do it. So I just wondering, like a professor, like in the code design, we have multiple systems. They may have different input and output. Like maybe the number of variables may different, the format may different. Then when we do our optimization problem, how can we make them compatible to each other, or we have some other methods to solve this?
Yeah, no, that's a good question. So when you look at these diagrams, some of the variables are hidden inside the boxes. What really matters is that these interfaces are playing well together. So in this particular case, you just need to make sure that whatever a component provides or requires is provided or required by another component, or it becomes a system level variable that you want to maximize or minimize or ignore. But you shouldn't think about, those are not necessarily input outputs. There's no direction in these diagrams, but it's rather, and also there is no time, by the way, right? There is not necessarily these wires are connected to time. They're not signals. But as long as you have agreement on these variables, then it's fine. Thanks a lot.
Thank you very much, Professor. We have one more question. You stated that design problems with implementations model is considered transparent. How does the direct feasibility relation model act as a black box between functionality and resources?
Well, I'm not sure I understand completely the question, but it's the reason why I say this is transparent or intellectually tractable is that if you look at classic multi-component design optimization from aerospace, for instance, the typical pattern there is to take a huge problem. You write down all the constraints, you write down all the objectives, you write down and you scalarize them most of the time. And you end up with a monster thing. Maybe it takes 4 or 5 pages to write down the entire problem in formulas. And then you don't know how to solve it because it's hard. And then you throw a genetic algorithm at it or some evolutionary algorithm. And you're never sure about the solution. This is not bad. So there are many things that are not nice there. One is you cannot find the real optima and so on. But another aspect is really transparency and intellectual tractability. If I am somebody that has to go and modify details of this problem, I don't know where to put my hands unless I am an expert in that particular domain. In co-design, although you have to understand some things, you can modify your boxes, right? And you can propagate whatever effect this box has on the entire network without a big effort. And true, you have to learn the language or say the specification language, but I feel that it's much more intellectually tractable than many of the things that are out there today. Of course, we are not yet completely intellectually tractable, right? But that's what I mean when I say transparent.
Thank you so much. There is one last quick question in the chat. Would you have time to answer?
Sure, absolutely. Yeah.
Okay. In the orchestration code design example, were all the components and wiring designed by the human, or did the code
That's a
design
great
facilitate machine-assisted algorithm design?
That's a great question. I always get it, and I like it because it's one of the active areas. Yeah, so right now you design the architecture yourself. So it's typically given by existing architectures. There are two answers to your question. One is the short answer is yes, you can. There is something we're doing where you're trying to come up automatically with an architecture given a problem. So when I say architecture, I mean these diagrams here. And the more technical answer is coming up with an architecture actually can be thought of a problem itself. So you can think of all of these architectures as elements of a partial order in themselves and elements of a wire. And now, depending on what you care about in your architecture, you might compare different architectures with each other. And so that could become a design variable. A super simple example is whether you want to do end-to-end or you actually want to do planning, perception, control, right? When do you want to do one or the other? What does this depend on? Compute, data, training time, these kind of things, right? You can formulate this problem with this language. So yeah, definitely, it's an active area.
Thank you very much, Professor, for this seminar.
Thank you all for organizing it, and please keep doing this because I want to see more recordings in the future. Thanks, everyone, and feel free to reach out to my email. You find it on my website here. So if you have any questions, feel free to reach out.
Thank
Thanks
you.
a lot.